Okay, hello everyone in a new video. So we have reached part 11 of chapter 5, which is the chapter of kinematics for grade 11 students. So now in this one we'll complete the explanation of this chapter, and we have reached section number 4, which is given by the circular motion. So previously all the discussion that we have done is on rectilinear motion. So now what as motion in 2 dimension, which can be decomposed into rectilinear motion along the x-axis and the y-axis. So what about the circular motion? So let me say that a motion is said to be circular when the trajectory represents a circle. So previously we have seen that whenever the parametric equations of x and y includes cosine and sine, then the trajectory is may be circle. So, and in this case we can distinguish between two types of motion that are given by UCM and UVCM. In this case, let me say we can consider two types of motion. The first one is UCM, uniform circular motion. And as for idea number 2, the other type is given by UVCM, uniform varied circular motion. So before we enter into discussion between the UCM and the UVCM, let's consider a circle. So first let me start by representing the x-axis and the y-axis. So suppose this is a circle and this is the x-axis. So this is the positive direction of the x-axis, this is the positive direction of the y-axis. Here x and y represent physical quantities that are given by the position. And suppose that this is the origin O, this is the unit vector I describing the x-axis, and this is the unit vector y, a j, describing the y-axis. And here suppose that we have a point M moving along the circle of radius r. Then let's say M moves along a circle of center O and radius r. So previously we have seen whenever we have the parametric equations we can determine the center and the radius. So and let me say that m can move in two directions. So m can rotate like this. So this direction is said to be the anti-clockwise direction. So the first one is given by the anti-clockwise. So this is said to be the anti-clockwise direction if m is moving like this. Right. So if m is moving in this direction, this is said to be the anti-clockwise direction because it's moving in a sense opposite to the hands of the clock. And for the clockwise direction, clockwise is said to be like this. In either case, we can define the angle theta to be the angle between the x-axis and the line adjoining OM, or the vector OM, which represents the vector r, the position vector. So let me say also if m so recall that in case of rectilinear motion, the position is said to be positive or negative depending on the orientation of the axes. And here let me say before we discuss the clockwise and the anti-clockwise direction, or let me say here the anti-clockwise direction is said to be the positive direction. So this is positive. So always we need to distinguish between positive and negative direction. And the clockwise direction is said to be the negative direction. And we are interested in defining, so let me say we are interested in defining position, speed, and acceleration in terms of angular quantities. So let's start with the position. So here we have the position. speed and acceleration, speed or velocity. As for the position, it's clear that theta, the measure of the angle in radians with respect to the x-axis, will represent the position. So theta is said to be the angular abscissa expressed in radians. As for the speed will be represented by omega. So this is given by the angular speed or angular velocity expressed in radians per second. So the symbol of radians is rad. And as for the acceleration, then it's given by alpha, given by angular acceleration, okay, which is given by radians per second square. Okay, so the point I'm moving along the circle is described by the position which is given by the angular, sorry, let me say that theta is the angular position, not the angular abscissa. So as the point M moves along the circle, we can define the angular position with respect to the x-axis. Now M can move at different speeds, and this is described by the quantity omega, which is the angular speed, and this speed can vary, representing the angular acceleration, which is alpha. So in this case, now we can talk about the UCM and UVCM. So UCM, so let me say if alpha is 0, so if the angular acceleration is 0, which means then omega is equal to a constant. Okay, then in this case, then the type of motion is UCM. Now if alpha is a constant different than 0, then omega varies with time. Then the type of motion is UVCM. And now we are ready to discuss UCM and UVCM separately and compare them with the URM and UVRM. Okay, so let's start by section 4.1, which discusses the UCM. So let me say that section 4.1, uniform circular motion then a motion is said to be a uniform circular motion if the trajectory is a circle and the particle is rotating at a constant angular speed. So let's consider the circle. better to draw them again. So this is the angle theta, this is the origin O, this is the unit vector I, this is the unit vector J, this is the radius R. So suppose that M is moving in a certain direction, so the anti-clockwise direction is said to be the positive, the anti-clockwise direction is said to be the negative. So recall that in the case of URM, the equations are given by x is equal to vt plus x0. Now v is equal to a constant and the acceleration is 0. Based on these equations, we will try to deduce the equations of the UCM related to the angular quantities. So in this case, in the case of UCM, now recall that, so x represents the position. For the circular motion, the position is given by angular position, which is theta. Now the speed is given by the angular speed, which is omega, and as for the acceleration, it's given by the angular acceleration, which is alpha. Then in this case, for UCM, the quantities or the relations are given by theta is equal to omega t plus theta 0. Now v represents omega. Omega is equal to a constant, and the angular acceleration is equal to 0. And we are done with the UCM. Okay, so we have deduced these quantities by comparing to that to URM. And here no need to consider between, okay, recall that this represents along one direction. If we are considering two directions, we need to distinguish between the x component and the y component. Here no need to distinguish between the x component and the y component. For this reason, we have one to the angular quantities or angular coordinates. Okay, so here no need to distinguish between theta x or theta y. Theta is theta, we are measuring it with respect to x and y. Okay, so these are the equations of UCM. So whenever we identify that the type of motion is UCM, then we can directly use these equations. Okay, now we can ask, okay, and let me also explain the following. So how can we relate these quantities to the previous quantities? So we know that we can also define the position. So we can also talk about the position x, the velocity v, and the acceleration a. So how can we relate x, v, and a with theta, omega, and alpha? So first of all, let me define a new quantity which is given by s. So let me say that s is the angular abscissa. So what does s represent? Now if you consider this point, the point m1, and another point which is the point m2, we can measure the distance along the arc from m1 to m2. So now if we cut this point and this point and we stretch this arc will be given by a straight line, which is given by m1, m2. The distance of this segment is given by s, which is the distance of this arc. So s is the angular abscissa. So now after we have defined s, we can relate s and theta. So in this case, s is equal to r multiplied by theta. In this case, the speed is equal to r multiplied by omega, and the acceleration is equal to r multiplied by the angular acceleration. So these relations are very important that relates angular and Cartesian quantities. Okay, now we need to discuss the following. So S is clear, R is clear, theta is clear, omega and alpha as well. What about V and A? What do they represent? Here we need to distinguish between the X component and the Y component for any quantity. So notice that S is a distance from point M1 to point M2, so no need to distinguish between X and Y. Now what about V and A? Actually here V, in this case, V is given by the square root of Vx square plus Vy square, so this is extremely important. As for the acceleration in this case, acceleration here is a bit tricky. This acceleration is the tangential acceleration. So AT is the tangential acceleration. Why? Because now let's consider the point M moving along the circle, okay? Okay, let's consider the point M moving along the circle. Let me erase everything. And suppose it's moving in the positive direction, which is anti-clockwise. Okay, so let me specify different positions of the point M. So suppose that this is the point M1, this is the point M2, this is the point M3, this is the point M4, and this is the point M5. And let me in each case represent the velocity vector v. So we know that v is tangent to the trajectory. So in this case, the velocity v1 is given by this. In this case, the velocity vector v2 is given by this. In this case, the velocity vector v3 is given by this. And in this case, the velocity vector v4 is given by this. And v5 is given by this, okay? So as you can notice, as the point M moves along the circle, the direction of the velocity vector changes. Let me here specify the following note. And I need to leave some space because I need to add additional formulas. So let me say the following important note. As the point M moves along the circle, the direction of the velocity vector at each instant changes. So what does this mean? We know that acceleration is due to change of direction and magnitude, which represents the speed of the velocity. So in either case, if the type of motion is UCM or UVCM, we have acceleration. So in both cases, UCM or UVCM, we have acceleration, which is the normal acceleration due to change in direction. So what I wanted to say that circular motion can be either UCM or UVCM. In the case of UCM, An is always given by V square over R, which is different than 0, and V is equal to Vx square plus Vy square. But as for the tangential acceleration, it's given by 0. In the case of UVCM, An is equal to V square over R. This is independent whether UCM or UVCM. And in this case, the tangential acceleration is different than 0. So what distinguishes UCM from UVCM is that UVCM we have varied motion, but the varied motion is due to the variation in the tangential acceleration and not the normal acceleration, okay? So although here what I'm saying is, so if alpha is equal to 0 and alpha is related to the acceleration but not any acceleration to the tangential acceleration, this is equal to 0 in the case of UCM, okay? But we can, although that AT is equal to 0, but this doesn't mean that the total acceleration is 0. So the total acceleration A, which is given by AX square plus AY square, is different than 0 because we can talk about the normal acceleration, which is due to change in speed, which is given by a change in direction, which is given by V square divided by R, okay? So whenever I say V without any components, we mean V that the speed, which is the square root of Vx square plus Vy square, which is the magnitude of the velocity, okay? So although the motion is UCM, so the angular acceleration is 0, but this doesn't mean that the acceleration itself is 0. So recall that the acceleration is given by ax square plus ay square, which can be decomposed into normal acceleration and tangential acceleration. So the normal acceleration exists because there is a change in the direction. However, in this case, the tangential acceleration is 0 because the speed along the circle is 0. Okay? So this note is very important. Now, as for the UVCM, so now we are in section 4.2. Uniform, varied, circular motion. Then a motion is said to be a uniform, varied, circular motion if the trajectory is circular and the angular speed and the particle is rotating at a constant angular acceleration, which means that angular speed varies with time. So before I move to this section, I need to add additional formulas here. So let me add them here. Delta theta, which is the displacement, is given by theta minus theta 0. Okay. Omega, which is the angular speed, is equal to 2 pi f, in which f is the frequency. And the frequency and the period are related via the following formula, that the frequency is equal to 1 over the period. Okay. And that's it. Now, so let me in this case consider also the system x-axis and the y-axis. So this is the x-axis, this is the y-axis. Now suppose that this is the origin O, this is the positive direction of the x-axis, positive direction of the y-axis, this is the unit vector I, this is the unit vector j, this is the point M moving in the positive direction and anti-clockwise. So this is the radius r, this is the angular position, which is theta. Now okay, so we need to identify this type of motion using equations. Recall that in the case of UVRM, we have that x is equal to half at square plus v0t plus x0. v is equal to at plus v0, and the acceleration is equal to a constant. Now in the case of UCM, we can deduce the equations of UVCM by comparing with these equations. So in the case of UVCM, we know that acceleration is being compared by alpha, speed is being compared by omega, position is being compared with theta. So in this case, theta is equal to half alpha t square plus omega 0 t plus theta 0. Omega is equal to alpha t plus omega 0, and we also have that alpha is equal to a constant. Recall that here in this case we have another important equation, which is given by v square f minus v square I is equal to a to ad. So we can also write, if this is the angular abscissa, which represents s, the distance from this point to this point, we can say that also omega square f minus omega square I. So this is equal to, okay, let me discuss this formula later. Let's keep it to another part. So these are the equations. We can write it here. So omega square f minus omega square I is equal to 2 alpha delta theta, which is the displacement. Okay. So we are done with these equations. Let me erase them. So now we can relate these equations, these angular quantities, to the Cartesian quantities by saying that S is equal to r theta, V is equal to r omega, and a is equal to r alpha, and here we need to be careful that this a represents the tangential acceleration, in which v is equal to square root of vx square plus vy square. A is equal to square root of ax square plus ay square. Also a can be written as square root of an square plus av square, at square. Moreover, the normal acceleration is always given by v square divided by r. We can also define all other quantities that we have defined in case of Cartesian. For example, one of them is given by u tangential, is given by velocity over the speed, etc, etc. We have a lot of equations. Okay, and what else we can say about this? So basically this is it for the UVCM. So if you want to represent the position, the velocity, and the acceleration, the position vector will be this. The velocity vector will be tangent to the trajectory like this. So this is v. As for the acceleration, the normal acceleration is toward the center. This is the normal acceleration. The tangential acceleration will be tangent also to the trajectory. And as for the total acceleration, is the completion of the parallelogram of diagonal A having sides A tangential and A normal. So basically this is it for the circular motion. Now let's solve the following exercise as a direct application on what we have explained. They are telling me two particles A and B move along circular trajectories. The angular abscissa of A and B at the instant t are given by theta A is equal to 4t plus 4 and theta B is equal to t square plus 2t plus 1. So before we start studying the type of motion, let me write here on the scratch the UCM and the UVCM equation. So in the case of UCM, we have the theta is equal to omega t plus theta 0. Omega is equal to a constant and alpha is equal to 0. And in the case of UVCM, we have that theta is equal to half alpha t square plus omega 0 t plus theta 0. Omega is equal to alpha t plus omega 0, and alpha is equal to a constant. Now in number 1 they are telling me motion of A, part 1. So specify the type of motion of A. So notice that the angular position is linear in time. Whenever the angular position is linear in time, which means that the type of motion is UCM. So since theta A is equal to 4t plus 4 verifies the general form, theta is equal to omega t plus theta 0, then the type of motion is UCM. So whenever we have specified the type of motion, we can use these equations directly. Now in number 2, let me say, so deduce the angular speed and the initial angular abscissa. Okay, so by deduce it means that we need to use the previous part. Okay, so in number 1 we have specified the type of motion. So let me say since the type of motion is UCM, then we can use the following equations that are given by theta is equal to omega t plus theta 0, omega is equal to a constant, alpha is equal to 0. We are interested in determining the angular speed, which is omega. The angular abscissa here, notice that this is s. So here let me change this and make it so, because we don't know the radius, let me make it the angular position and let me change this and make it the angular position as well. Okay, so by comparing, so the given form is given by theta is equal to 4t plus 4. Here we are talking for sure about theta a, but I will not put the labels. So by comparison, we have that omega is equal to 4. The assignment of omega is given by radians per second, and in this case the initial angular position is given by theta 0 is equal to 4 radians. Okay, now number 3, they are telling me to calculate the angular displacement. By angular displacement they mean delta theta. So delta theta, which is equal to theta minus theta 0. This theta is computed at the instant t is equal to 4 seconds. So this is equal to theta t is equal to 4 seconds minus theta 0. Theta 0 is equal to 4 radians. Now theta as t is equal to 4 seconds is equal to, now we replace time by 4 seconds, we have that 4 multiplied by 4 plus 4, so this is equal to 16 plus 4, so this is 20 radians. Now this is equal to 20 minus 4, which is equal to 16 radians. So this is it for part 1, the motion of A. Now as for the motion of B, part 2, and number 1, they are telling specify the nature of motion. So notice that in this case the position is quadratic in time. Whenever the position is quadratic in time, this means that the type of motion is Ucm. Since theta is equal to t squared plus 2t plus 1 verifies the general form, theta is equal to half alpha t squared plus v0t plus theta 0, then the type of motion is Uvcm. Now in number 2, they are telling me deduce the angular acceleration, initial angular speed, and the initial angular position, and by deduce it means that we need to use the previous part. In the previous part we have to specify the type of motion, so let me say since the type of motion is Uvcm, then we can use these equations directly that are given by theta is equal to half alpha t squared plus v0t plus theta 0, omega is equal to alpha t plus omega 0, alpha is equal to a constant. So in this case the given form is given by theta is equal to t squared plus 2t minus 1. So we are interested in determining the angular acceleration, which is alpha. So by comparison, half alpha is equal to 1, then alpha is equal to 2 radians per second square. So I don't remember that I have defined the unit of alpha. Now I will get back and define them. So what about the initial angular speed? So okay, this is omega 0. This is omega 0 here, okay. So as for the initial angular speed, comparing the linear terms, we can see that omega 0 is equal to 2 radians per second. And as for the initial angular position, this is given by theta 0 is equal to minus 1 radians, okay. And finally in number 3, they are telling me to calculate the angular speed. By determining the angular speed, we are interested in determining omega, which means we need to write it in the following form. So omega is equal to alpha t plus omega 0, but the value of alpha is equal to 2, and the value of omega 0 is 2. So the angular speed, because it's UVCM, it varies with time. As for the angular displacement, which is given by delta theta, which is equal to theta minus theta 0, this is computed at the instant t0 is equal to 0, which is minus 1. As for theta, in this case theta is equal to theta computed at the instant t is equal to 4 seconds, which is equal to 4, so we are referring to this one, 4 to the power 2 plus 2 multiplied by 4 minus 1, which is equal to 16 plus 8, which is 24 minus 1, 23. Make sure of the calculation, 16, okay. So this is 23 radians, so in this case this is equal to 23 plus 1, which is equal to 24 radians. Okay, and here let me specify the units of the units of the quantities. So let me say the following note, that the unit of theta, so the brackets represents the unit, unit of omega is radians per second, unit of alpha is radians per second square, unit of delta theta is radians, okay, unit of the frequency is hertz, okay, and the unit of the period is second. And let me make the following also clear. So theta is called to be the angular position or the angular abscissa, whereas S is said to be, so I usually refer to this one in order not to mix with the angular abscissa, but as for S, it's said to be the curvilinear position or curvilinear abscissa, okay. So let's fix these. S is expressed in meters because S represents a distance, okay. Now, so in this case, no need to change the question in the following form, this is good, okay. So in this case, angular abscissa represents theta, and the initial angular, okay, angular abscissa represents theta, initial angular abscissa represents theta 0. So that's it for me in this video, guys. In the next part, we'll complete exercises on this chapter.